Hi, my name is Sadman Binzaman. This is EL6303, assignment 6, question number 1. X and y have joint density function equaling bxy from the interval 0 less than equal to x less than equal to y less than equal to 1, 0 otherwise. For our convenience, there's a quick sketch of what our density function should look like, and we're interested in the shaded region. Part A of the question asks us to find b from bxy. Assuming that x and y is a valid joint density function, we can set the double integral to equal to 1. So the integral from 0 to 1, the double integral of bxy dy dx should equal 1. B being a constant, we can take it outside of the integral, and we can get the integral from 0 to 1 of x, the integral from x to 1 of y dy dx equals 1. First, we'll focus on the second integral, the integral of y dy, which evaluates to 1/2 y squared x to 1. 1/2 being another constant, we can bring that outside. We get b over 2, the integral from 0 to 1 of x, y squared x to 1 dx equals 1. After we evaluate this integral, we'll have it in terms of x, which gives us b over 2, the integral from 0 to 1 of x times 1 minus x squared dx equals 1. We can distribute the x. We get b over 2 equals the integral from 0 to 1 of x minus x cubed dx, which equals 1. We can take the integral of this inside of the x's, which gets x squared over 2 minus x fourth over 4, going from 0 to 1. That evaluates to, after doing a quick little algebra, b equals 8. Part 2 of the question asks us to find and sketch the marginal density functions f of x and f of y. F of x is the integral from x to 1 of 8xy dy, where we know that 8x, we're uninterested in 8x because we're integrating in terms of y. We can bring that outside. So 8x times the integral from x to 1 of y dy, that evaluates to y squared over 2, ranging from x to 1. After doing the quick arithmetic, we get that equal to 4x times 1 minus x squared. The marginal density y, f of y, equals the integral from 0 to y of 8xy dx. In this case, we're not interested, since we're integrating the x's, we're not interested in the y. We can bring that outside. So we get 8y, the integral from 0 to y of x dx, which equals the integral y squared over 2, 0y, which values to 4y cubed. These are the quick sketches of f of x and f of y. Part C of the question asks us to prove or disprove that x and y are independent. We need to know that x and y are independent if and only if f of xy equals f of x times f of y, and that does not hold up in our case because 8xy does not equal 4x times 1 minus x squared times 4y cubed. Thus, in our case, x and y are not independent. Part D of the question asks us to find the expected value of x, the expected value of y, and the expected value of xy. The expected value of x equals the integral from 0 to 1, x times f of x dx. From our previous parts, we know that f of x equals 4x times 1 minus x squared. We substitute that in. Now we're looking for the integral from 0 to 1 of x times 4x times 1 minus x squared dx. That evaluates to 4x squared, 1 minus x squared dx, which equals to 8 over 15. Likewise, for the expected value of y, that equals the integral from 0 to y times f of y dy, which equals the integral from 0 to 1. From an earlier part, we know that f of y equals 4y cubed. So we have the integral from 0 to 1 of y times 4y cubed dy. That multiplies that to the integral from 0 to 1 of 4y to the fourth power dy, and that evaluates to 4 over 5. The expected value of xy is the double integral of x times y times f of xy dx dy. We set up our integrals. The one pertaining to the dx is going to range from 0 to 1. The one pertaining to the y is going to go from x to 1. So the integral of xy, 8xy dy dx, 8 being a constant, we can bring outside, equals 8 times the integral of 0 to 1 of x squared, and the integral of x from x to 1 of y squared dy dx. This middle term is related to the y, and the outers are for the x. That equals to, now we're just going to deal with the y's, so that equals 8 times the integral from 0 to 1 of x squared the integral for the y's evaluates to y over cubed over 3, going from x to 1. That evaluates to 1 minus x squared. So we have 8 over 3 times the integral from 0 to 1, x squared, 1 minus x squared dx. Now we're interested in evaluating the integral for the x's. So that equals 8 over 3, the integral from 0 to 1, x squared minus x fifth dx, which becomes 8 over third, integral of x squared over 3 minus x fifth to fifth, going from 0 to 1. Make our substitutions, we get 8 third times 1 third minus 1 sixth, and that equals 4 over 9. Part E of the question asks us to prove or disprove if x and y are uncorrelated. We need to know that x and y are uncorrelated if and only if the expected value of xy equals the expected value of x times the expected value of y. Again, in our case, that does not hold true. 4/9 does not equal 8 over 15 times 4 over fifths. Thus, x and y are not uncorrelated. Part F of the question asks us to find and sketch the conditional density functions f of y given x and f of x given y. The conditional density function f of y given x equals f of xy over f of x, which we know equals 8xy divided by 4x times 1 minus x squared, which simplifies to 2y over 1 minus x squared for the interval x being less than equal to y, less than equal to 1. We can do a quick check, and we know that the integral from x to 1 of fy of x dy, fy given x dy equals the integral from x to 1, 2y over here, 2y minus 1 minus x squared dy. We're not interested in the x's now, so anything having x's or a constant we can bring outside. So 2 divided by 1 minus x squared, the integral going from x to 1 of y dy equals 1. Here's a quick sketch. Remember, we're only interested in y when it's going from x to 1. So anything before that we're not interested in. So we're only interested for here. X equals x over 1 minus x squared, and 1, we get 1 minus x squared. 1 divided by 1 minus x squared. Finding the conditional density function of fx given y is pretty similar. We have the function x and y over f of y, which equals 8xy over 4y cubed, which simplifies to 2x over y squared for the interval 0 less than equal to x less than equal to y. We can check this out. The integral from 0 to y of the function x given y dx, which equals the function 0 over y, 2x over y squared dx. In this particular case, we're not interested in anything that has to do with y, so we can bring that outside. So 2 over y squared equals the integral from 0 to y of x dx, which equals 2y squared, x squared over 2, going from 0 to y, and that equals to 1. Over here is a quick sketch of what our conditional density function should look like. We're only interested in x as it ranges from 0 to y, and at 0 it equals 0, at y equals 2 over y. The final part of the question asks us to find the expected value of y, capital Y given x. That equals the integral from x of 1, y times the function, times the conditional density function y given x dy, which equals the integral from x to 1, y times 2y minus 1 minus x squared. This value we got from our previous part, part F, when we're asked to calculate the density function of fy given x. And that equals 2. Again, since we're integrating y, anything that involves x we're not interested in. We can bring out the 2 over 1 minus x squared and integrate from x to 1 of y squared dy. We get 2 times 1 minus x squared, y cubed over 3, x to 1, and that evaluates up to 2 times 1 minus x cubed over 3 times 1 minus x squared. Expected value of capital Y given x is the same thing, except we just switch our small x to capital X. Now, calculating the expected value of x given y is the integral from 0 to y of x times the conditional density function of x given y, which equals the integral from 0 to y, x times 2x over y squared. Again, this we got from this previous part. In this case, we're not interested in anything that has to do with y, so we bring that outside. So 2 times y squared, the integral 0 to y, x squared dx. This integral evaluates to x cubed over 3, going from 0 to y, and that eventually simplifies to 2y cubed. And like the previous part, the expected value of capital X, capital Y it goes to 2 capital Y over 3. Thank you.